Okay, yeah, I guess we can start. We're very happy to have Vladimir talking about dualities between fermionic theories and the Potts model. And please, Vladimir, the stage is yours.
Thank you very much. Yes. So indeed, I will talk about this paper. And please, of course, interrupt me if you have any questions. Okay, so there is this interesting system that was discussed in this paper. By the way, can you see my cursor, the mouse?
Yes.
Yeah, okay, good. So there's this system that was described in this paper, which has several different but equivalent descriptions. So one is a random statistical system of spanning forests, random forests on a graph. The other is a Q goes to zero limit of Potts model. And another one is the OSP1-2 sigma model. And in this talk, we'll discuss generalizations of each of these items, and we'll also mention how they're related. So just the outline. First, I will give some motivation from physics, at least some context in physics. Not all of them, of course, where this appears. This will just be an overview of some of the related theories, just for interest. Then in the second part, I'll be much more concrete, and the main point that I will make is that there is an equivalence between a large class of fermionic theories and the Potts model as well. This will be a generalization of this example. And then I'll apply to, again, a generalization of the OSP1-2 case to OSP1-2M. Okay. So indeed, let me start by mentioning several cases where these theories in general, such theories of anti-commuting variables appear in physics, okay, at least some context. And always, just a comment, always when I say fermionic, sometimes I say fermionic, I really just mean anti-commuting. So there is no reference to spin or anything like that, okay? And many systems will be on a lattice, so I don't discuss spin here. So one way to motivate this is just as a generalization of the famous ON model. So in analogy to the 5 to the 4th theory for n commuting variables, there is a related theory where we take n anti-commuting real scalars. So this system is going to have SPN symmetry, and it's something like this 5 to the 4th interaction, just that we use the anti-symmetric symplectic form omega. Or another way to write it, much simpler, is just to take n over 2 complex anti-commuting variables or complex fermions, theta and theta bar. So I here goes from 1 to n over 2. N must be even always. And then we just get this sort of 5 to the 4th interaction. And this theory below 4 dimensions is an IR fixed point, just like the usual ON theory. Now, one motivation for this system, specifically this theory that I wrote here, one motivation for that is the DCFT correspondence, where we have quantum gravity living on a space with positive cosmological constant is supposed to be related to conformal field theory, Euclidean conformal field theory living in the future boundary. And the theory appears in this context because there is this conjecture by Aninos, Hartmann, and Strominger that the singlet sector of the 3-dimensional critical system that I just wrote of these anti-commuting variables is related. This lives here in the future. This is a CFT, and it is related to a theory in the bulk, which is a theory, what's known as Vasilyev's theory. It's a theory of infinitely many higher spin massless fields in the Sitter 4. Okay. Now, where does this conjecture come from? It's actually very simple. It's just basically an analytic continuation of this known, well-known ADS-CFT case. So here it's ADS-CFT, where we have the singlet sector of the critical ON model. This is this conjecture by Klebanov and Polyakov. At large n is related to the same Vasilyev's theorem, but in ADS4. So how do we go from ADS to DS? We just need to switch the sign of the cosmological constant. Now, in vector models, n, the number of fields, is related to the cosmological constant lambda by 1 over lambda times g Newton. So if we want to switch the cosmological constant, all we need to do is to take n to minus n, basically, by this relation. And what it will do is that it will take ON essentially to SPN. So how do we do that? There is a simple known argument, which is that if we're doing vector models, then we know that in vector models, every loop, if we're doing a diagrammatic expansion, every loop gives us a factor of n, just by the fundamental that can run in the loop. We also know that in field theory, when we have a fermion, every loop gives us a factor of -1. So if we just turn the bosons into fermions, that will take each factor of n to a factor of -n. Okay, so that's why we go from the Owen model to this theory where we just change the bosons to fermions. Now this specifically is in 3-dimensional CFT and 4-dimensional de Sitter. What about higher dimensions? So the continuation to higher dimension was conjectured in this paper, where they say that there is a related theory that actually gives the same critical behavior. This theory is a theory of one boson, sigma, and again, this n/2 complex fermions, theta and theta bar. Here, it's not a quartic theory, it's a cubic theory with sigma theta squared and sigma cube interactions. And the claim of this paper is that while the previous theory has only, at least in 4 plus epsilon, is only a UV fixed point, the cubic theory that we write here has it flows in the IR to a fixed point, which is supposed to be the same. Okay, and this theory is defined between 4 and 6 dimensions, or at least below 6 dimensions. Okay, and as a test of that, what you could do, which was done in this paper, is to do 6 minus epsilon expansion in this theory, where it is weakly coupled, and see that all the scaling dimensions that you check actually do, at least at large n, with the theory with the quartic theory that I wrote before. Okay, so this is just another description of the same SPN critical system. Now, the idea basically is that if we take this theory now in 5D, this is an IR fixed point in 5D, this is supposed to be dual to Vasilyev's theory in DS6. Okay, this is just a generalization of the previous discussion. So the picture is that if we change the dimension D, below 4 dimensions, we have the quartic theory that has an IR fixed point, which is this SPN critical theory. And if we want to continue to above 4 dimensions, we have this cubic theory with the real boson in addition, that flows in the IR to the same critical point that just continues the same theory as here. Okay, if you want an analogy, this is like the Owen model, where we have the sigma model, the Owen sigma model. This above 2 dimensions is non-renormalizable, and the 5 to the 4th theory just provides, in a sense, a UV completion to that. It's just a theory that flows to the same critical point. Okay. Now, what about the case k n equal to 2? Okay, so now we start making contact with these OSP1-2 theories. When n equal to 2, the quartic theory doesn't exist, right? Because this theta bar, if we have only one theta and theta bar, the theta bar theta squared just vanishes, because these are fermions. So this theory doesn't exist, the quartic theory doesn't exist, but the cubic theory does exist. There's no problem to write sigma theta bar theta. So this is the only description that you have at n equal to 2 for this system, okay? I mean that there is no quartic description. And in the same paper, what they noticed is that if you look at 6 minus epsilon expansion, in the epsilon expansion, you see that these couplings G1 and G2 are not independent. They are related by this relation, okay? Because of this relation, the symmetry is actually get enhanced. The interaction is not just some random combination of these two interactions, but rather it combines to this form, which can be written also as this. Now, sigma squared plus theta bar theta, that's the invariant form of OSP1-2 supergroup. So this theory manifestly becomes, so there is an enhancement of symmetry. Rather than the SP2 symmetry that we had here manifestly, we see that in the IR there is an enhancement to the supergroup OSP1-2. Okay.
Sorry, can I ask?
Yeah, definitely, yeah.
Yeah, but so your cubic description now is valid also in this smaller than 4, or not?
Say again.
your cubic description is valid also in dimensions smaller than 4 or not? Now we're talking just.
Yes, that's right. That's right. In principle, it
Okay.
still flows to right. In principle, it still flows to an R fixed point, and I think it should also be valid indeed below 4 dimensions. It should just give the same. Yeah, that's right. It should just give the same critical point as the quartic theory for n greater than 2. It's just that it becomes very hard to solve because there is no weakly coupled description. Indeed.
I see, I see. And so in n equals to 2, you're saying it's very special because one doesn't exist, but the cubic theory, it's still gonna get something, right?
Exactly. The cubic theory does exist, and in fact, it's just another description of as I'll say in a moment, it's just another description of there is another OSP 1-2 invariant theory, which is the nonlinear sigma model. So it should give the same critical point as this nonlinear sigma model.
Okay. Okay. Thanks.
Yeah. Please ask if there are any questions. Please ask. So actually, there is another. Just let me say comment, just because you asked. There is another theory where instead of the thetas, you take basically you take commuting variables, like in the Owen model, and in another work we extrapolated from 6 minus epsilon actually to 2 dimensions. There is a critical point, and we show that it is actually related to a minimal model, basically. So, if you do the 6 minus epsilon expansion very well, you can even extrapolate to a very low dimension and get pretty nice agreement, which is a bit surprising. But okay, this is another story. Okay, good. So indeed, this is the exactly the system that I mentioned at the beginning, which is basically we get the OSP 1-2 invariance, which is also known to be described by a Q goes to 0 limit of the Potts model or random forests. And this was checked. So in this paper that I mentioned, they checked that when you do the 6 minus epsilon expansion, you get the scaling dimensions to agree with Q goes to 0 Potts or random forests. Okay. So this gives evidence that this theory, exactly this action, this is a Euclidean action with the 1 bosonic and 2 on 1 complex fermion. It gives in the IR a fixed point, which is the Q goes to 0 Potts or random forests. Okay, so this is a pretty nice check. Now we want to generalize this. Okay, so now we want to discuss in general OSP 1-2M supergroup. Okay. So as we just discussed, and as I said, n always has to be even. So instead of n, sometimes I'll write 2m, where m is an integer. Okay. So there is the OSP 1-2m sigma models, as we just mentioned, where the action is just the kinetic terms, but we have the constraint. So really the constraint is this one. This is, again, the same invariant form of OSP 1-2m. Now the thetas go from 1 to m. So I goes from 1 to m. So this is manifestly, of course, this theory is manifestly invariant under OSP 1-2m. This sigma model is clearly invariant under it. Now note that this equation has 2 solutions for sigma, this one and minus this one. And by definition, we include only this one. Okay, this is just the definition of this particular theory we discuss here. Now this sigma model, again, is not normalizable above 2 dimensions. But so it has a UV fixed point if you do 2 plus epsilon dimensions, okay? And you can ask, is there, similar to what we just discussed, right? Is there another theory that in the IR will flow to the same critical point that there's this OSP 1-2M symmetry? So for m equal to 1, we said what it is, right? It's this theory. What about higher m? We want to generalize this. So at higher m, Klebanov had a paper where he conjectured that this theory, it's just very simple to the one that we wrote previously, where you have still one commuting variable sigma, and now you have m theta and theta bars, okay? And the interaction previously, it was sigma squared plus theta bar theta to the power 3/2. So now there is just another power that guarantees that this is just some expansion of a finite number of terms that depend on sigma and theta bar theta. Now, the evidence that was given in this paper is similarly to what we mentioned in the m equal to 1 case. Specifically for m equal to 2 and 3, it checked that if you do the epsilon expansion below the upper critical dimension, you will get fixed points where the coefficients of the different terms conspire such that you get OSP 1 to M invariance. So it's not just some general interaction, but it's invariant under this. Okay, and the upper critical dimension is given by this formula. For m equal to 1, this is just 6, as we saw before. It's the cubic theory. And for higher m's, it's smaller. For m equal to 2, it's 10 over 3, and for higher and higher m's, it's smaller. Okay, so this also gives you a prediction for what is the upper critical dimension of the OSP 1 to m sigma models. It says that this is the upper critical dimension. And it would be nice to verify this. Okay, so this is something that needs to be verified. Okay, so now it's natural to us. So in the case of 1 OSP 1 to m, basically the m equal to 1 case, we know that there is this very nice Potts description, very known statistical system, and the random forest description. Is there anything like that also for general m, right? That's a very natural thing to ask, because then we can also study much better the system. And for the rest of the talk, I will just assume that the nonlinear sigma model, this one, and this theory give the same critical point. Okay, so we want to understand this OSP 1 to m systems. Okay, so that was just some motivation and the system that we want to study. And now I will be very concrete. Okay, we'll be very concrete about the system, and the basic claim is going to be that there will be an equivalence between a large class of fermionic theories and the Potts model. Okay. So let's define. Let's be very careful and just define the two sides of this duality carefully. Okay. So let's start with the fermionic theories. So as usual, we're going to specify, as done often, we're going to specify the theories of the fermions using a graph G. Okay. So the theory will live on a graph G. The graph G is going to have vertices V and edges E, okay? And without loss of generality, we'll assume that between any two vertices, there is at most one edge. So either there is an edge or no edge, okay? And so because it will just be the same for our interest. Now, the edges are going also to have a weight W. So between two vertices I and J, there is a weight W, Ij, that is just some number or anything, okay? So in particular, if Wij is 0, this is the same as having no edge between I and J. And then we define again, as known, the Laplacian matrix L, which is a V by V matrix. In the off-diagonal entries, you think about the indices I and J as labeling the vertices. So it's just going to be the off-diagonal element is just going to be negative of the weight between I and J. Okay, and the diagonal elements are defined such that the sum of the elements of every row and every column are 0. Okay, here I just give, to be very explicit, I just give one example. In 1D, if we take unit weights and the usual lattice system, okay, just of nearest neighbors connected by a line. Oh, yes, of nearest neighbors connected by a line. Then the Laplacian matrix takes this form. Okay, just we have a -1 because the weight is 1 between every two nearest neighbor, between this guy and this guy. Okay, and on the diagonal we have 2 just because every vertex has 2 neighbors. And then the sum of the rows and the columns is 0. This is just discretized Laplacian, and this is why it's called the Laplacian matrix, of course. Okay, now the Hamiltonian. The Hamiltonian is going to be defined by 2 terms. We are going to have a kinetic term and interaction terms. Okay. First of all, we need to introduce the antecommuting the variables theta and theta bar on every vertex. So we place theta and theta bar on every vertex I in the graph. The kinetic term is just a contraction of these vectors theta and theta bar with the matrix L, the Laplacian. This is just the kinetic term. Now, for the interactions, they are going to be specified by subgraphs gamma of the graph G. Okay, so for the duality that I will mention, it will be enough. I will mention why, but it will be enough to consider gamma to depend only on the vertices. So the edges are not going to be important. I will mention this in a second. So basically what we do is that for every subgraph gamma, we have an interaction with the coupling constant T gamma, and the interaction term is just the product of theta bar theta for every vertex of the subgraph. So in total, we're interested in a fermionic theory, which has this term theta bar L theta, and the interaction specified by the subgraphs gamma with the coupling constants T gamma. Okay. Is the fermionic theory clear? Any questions on that? Okay, just to make sure everything is clear. Now the pot side, on the pot side, we're going to place a pot's degree of freedom, sigma, on every vertex also. So again, the degrees of freedom live on the vertices of the graph, and sigma takes values as usual between 1 and q. Now the new ingredient that we'll introduce is a magnetic field with a direction that is also specified by a number between 1 and q, an integer. This is not going to be a dynamical degree of freedom. You can think about it as something fixed, some background thing. Now, the usual interaction in the POTS model, there are two kinds of interaction. One is the usual nearest neighbor interactions, the Kronecker delta, where if the two nearest neighbors have the same pot state, then we get 1, and otherwise we get 0. And always when I say nearest neighbor, I just mean two sides or two vertices that are connected by an edge. The other interaction is a similar interaction, but with a magnetic field. So you basically get 1 if your pot's degree of freedom is aligned with the direction of the magnetic field H, and 0 otherwise. Okay, and of course, the most famous example of pots is Q equal to 2, which is the Ising model, where the first interaction is the same as just saying that if the spins point in the same direction, we get a particular energy, and if not, we get another energy. And similarly, the second interaction just says that the energy depends on whether the spin is aligned along the magnetic field or not. So in the Q equal to 2 case, these interactions are very obvious physically. Okay. Okay, so now what is the claim? So the claim, as I said, is that there is an equivalence between all this large class of fermionic theories that I wrote that I introduced in the first part. Okay, so these are all of these. I mean, not the motivation, all the ones that I defined using all the interactions gamma. And on the right-hand side, we have a Potts theory, and we also take a Q goes to 0 limit, where the Hamiltonian is given by this. So I'll break it down in a second. So we just need to, this is just a partition sum over all the Potts degrees of freedom. There are nearest neighbor terms, as usual in the Potts model, okay, between the sigma and sigma j. So this is the notation of nearest neighbors. The strength of the nearest neighbor term depends on W, the weights of the graph. Okay, so similarly as here, L basically depends on the W. This term, this kinetic term, also depends on W. And then for every interaction term here, you get one interaction term here, where all the spins in the subgraph gamma are interacting with the magnetic field with this delta term. Okay. And the coefficient, the interaction strength, is depending on the same coefficient T gamma as we have here. Okay, there are some factors of Q that we will discuss later, but these are just some constants. Okay.
Sorry,
is the claim clear? Yes.
Yeah, is this what was already present in literature, or this is not related to the OSP 1-2, right? Yet. Or this is...
No, not yet. Right. This is just something completely general that I want to discuss, and I will prove it. Okay. This is a generalization of the known case of the OSP 1-2, but indeed it's a bit different. Here we have this magnetic field and so on. So this is another claim that I'm going to prove basically. Okay. And then we'll see how it's related to OSP 1-2M. That we'll discuss later.
Okay.
Okay, but at the moment it's very general. Okay, it's for any interactions like this. Okay.
Yeah.
Okay, so what is the strategy to prove it? So we're going to first find a random graph description for the left-hand side, for this side, the side with the fermionic variables. Okay, and then we're going to essentially show that the right-hand side by procedures generalizing the famous Fortune-Castellan, that is going to reduce to the same random graph description. Okay, So random graph is basically going to be an intermediate stage in showing that the left-hand side is equal to the right-hand side. Okay? And here we're going to meet all the spanning forests and so on, as in these seed seminars. So, okay, so I think, so indeed for this, let me first recall briefly, I think there was a previous talk by Andreas Portiello, so let me just briefly recall what was shown in this paper. Okay, I'll be brief, but I will also give the basic idea. So the basic idea is that suppose that we first have only the kinetic term, this theta bar L theta, and we can also have an insertion of theta bar theta at a fixed vertex I. Of course, without this insertion, we just get determinant of L, which is 0, because all the rows are 0, the sums. But if we have this insertion, we're going to get similarly the determinant of L, where we remove one row, the row with index I and the column with index I. Okay. And this determinant is known by Kirchhoff's theorem to be given by the sum over all the spanning trees and the weight of the tree. So always when I say weight of the graph, I just mean the product of all the weights of the edges in this subgraph T. Okay. And here I just remind very quickly that spanning means that T has all the vertices of the full graph. Forest means that there are no cycles, and trees means that they are connected with no cycles. Here I just show an example where we have a two-dimensional lattice, and the subgraph T is shown in blue. Okay, and you see that this is indeed a spanning tree. And just one comment is that we can think about this I that appears here as marking a root at the position I along this tree. Now, of course, the tree is spanning, so it covers all the vertices, so you can choose any of them, and indeed the result is going to be independent of I. This is the same result, whatever I you choose. But it's just convenient to think about it as a tree with one marked point at I. Indeed, there is a very simple generalization where this thinking is useful, because if we have R insertions of theta bar theta at R different vertices, we're going to get a sum instead of spanning trees, we're going to get a sum over spanning forests in G. And the spanning forests are marked with roots at exactly the R points, I1 up to IR. So that means that at every connected component of the forest, every tree basically, there needs to be exactly one of these vertices. Okay, these are the only allowed forests that we're going to include in the sum here, and everyone is assigned the same weight. Okay. Now, here is a very slight, let me mention a very, very slight generalization of the claim that generalizes this in this paper. So now, just for the moment, for every subgraph gamma that describes an interaction, as we had before, now for a second, I am going to restore the weights of the edges. Previously, I didn't write them. I'll say in a second why. But now let's restore them just for a second. So now we have for every interaction gamma, we have Q gamma, these deformations, these interactions, which are the product of theta bar theta over the vertices and the weights of the edges. And now I allow it to be not necessarily connected. Okay, this is the slight generalization. What is it given by? So this is given by generalization of what we just saw. It's going to be a sum over all spanning subgraphs composed of a particular number of disjoint elements, HI. So HI are disjoint, but they're not necessarily connected. Okay, and they were given the weights of the edges. And now we also need to give a weight for every HI. What is the weight of HI? W of HI is just going to be the sum over all the markings with the interaction. And we say that gamma marks HI if gamma is contained in HI. It's a subgraph of HI. Every connected component of HI contains exactly one connected component of gamma. Okay, and there are no cycles in HI beyond those that already exist in gamma. Okay, this is just a generalization of the forest or the forest condition. There are no new cycles basically. Now, this may sound like a complicated description, but it's very simple, right? All it says is that you need to sum over all the spanning subgraphs, okay, that introduce no new cycles. And the only condition is that you mark the subgraphs with the interactions. such that every connected component of the subgraph contains exactly one connected component of the interaction. Okay, here I show an example. If we take one interaction which is composed just of two vertices, I and j, with some coupling t, and another interaction which is composed of one vertex only, k. Okay, let's fix ij and k. And this one is coupling s. So here I draw the vertices I, j, and k. So you see that in this example, there are three connected components, three trees. Okay, there are only trees here. There are no loops. This, and this. And every tree is marked by exactly 1 point. Okay, so here there is only 1, here there's only j, and here there's only k. Now, I and j belong to the same interaction, but it doesn't matter. It's still, what needs to be important is that every connected component has only one connected component from the subgraph. Okay, is it clear? Any questions about this description? Okay, now all I want to say is that the inclusion of this factor of the product of the edges, we don't really need to do that, right? Because we can just, this is just a constant. It's not a dynamical variable as this one. So we just absorb it in the coefficients t gamma. So we can, without loss of generality, we can only get a larger class of interactions or the same ones if we do not include this. Okay. So for us now, gammas are going to be subgraph consisting just of vertices, as in this example. Okay, only vertices, no edges. In particular,
but if you don't,
yeah,
if you didn't put any weight from the beginning, then you cannot have any kind of dependence over the point, right? Is that what you said in the previous slides?
Say again, say again.
So if you didn't put any weight since the beginning, you couldn't have any dependence over the single dots, right? Or not?
I mean, what do you mean no dependence on the dots?
Like in the case before, you were saying that there was no dependence over the I.
Oh, I see what you're saying. Okay, good. I think it can still depend on the eyes. You mean like here, in this case?
Yes, yes.
In this case, it's true that it didn't depend on the I, but if you have several I's and J's, like here, I think it can, I would assume that it might depend on the I and J. I would need to think about it. Because in general, let's see. Can it depend on them? It's a good question. Sorry, okay, let's think about it for a second. Yeah, it's not obvious that it doesn't depend on them, right? Because it depends, it might depend where you put, since here you have 2 points, for example, I and J, right? And G can be any graph, right? It might matter whether you put, for example, I and J on the same connected component of G or not, and so on, right? It might be important.
I see, I see, okay.
Yeah, previously you had only 1 point, so it didn't matter, but here you can have several points.
I see.
Yeah.
Okay, thanks.
So now just to demonstrate this point that it doesn't matter whether you put the W's or not, here's just another way to think about it. And I will, if there is time, I will use it actually later on. The idea is that this is like a consistency check on the formula that we gave here. Suppose that you compare a subgraph where you have only 2 vertices I and J to a subgraph where you have 2 vertices I and J, and you include the edge between them. So what is going to happen? They will give the same result. Why? Because for every subgraph, you're going to sum over all the subgraphs H of G, right? Now, for every subgraph that this guy will mark, there will be a corresponding subgraph that this guy will mark. Okay, so there's going to be a one-to-one correspondence between them. For example, here I show an example of 2 trees. They are not connected, so you can mark I here and J here. That will be good, right? There is only 1 point at every tree. That's good. So this will mark this, it will contribute to this, but this will not, because this edge is not part of the graph, okay? However, if we just add this edge, then of course this guy now will mark this one, because you can put here I and J and the edge, and this is a connected subgraph of this connected one. So this marks this, but the first one does not mark this, because if we just place I and J without the edge between them, we have two connected components inside one. And we said that every connected component must have exactly one connected component. Okay? So since we sum over all the h's, we're going to get that this one will have the same contribution as this one. Okay? This is just another argument for why, and the consistency check on the formula for why we can forget about these w's. So we really lose no generality here. Okay, so now let me summarize what is the left-hand side. So now we describe the left-hand side of the duality. We have this fermionic theory where we include in the interactions, we include no edges, only these vertices I. Okay? Since we include no edges and only vertices, of course, there are no loops inside gamma. These are just edges. And so in the right-hand side, when we sum over h's, we just need to sum over spanning forests. So we again reduce in the, basically, this completely general case, we reduce only to sum over spanning forests. Okay? So the graph description of this fermionic theory is given by the following simple rules. You need to sum over all the spanning forests. For every forest, you need to sum over all the markings with the interaction, such that a simple rule, every tree of the forest includes exactly one vertex. Okay, just as, let me show you this, just as in this picture, every tree has one point. Okay. And then the value we assign for every such thing is the product of the couplings that you used and the weight of the subgraph, just the product of the weights of the subgraph. And that's it. Okay, this is a very simple description. Okay, so now we can prove the claim. So we've shown that the left-hand side, the fermionic theory, is given by this spanning forest description with markings by these points. Now let's see what happens for the right-hand side. So let's look at this. So the right-hand side, the Potts model, we wrote here. I just copied it. It's just the limit of q goes to 0 of this Hamiltonian. Now we're going to use this simple relation. For any delta, for any chronicle delta, e to the log of 1 plus any constant times this delta is going to be given by this. Okay, this is very simple to see, because if the delta is 1, we're just going to get 1 plus c, same on the left-hand side. And if the delta is 0, we're just going to get 1, and that's also true on the left-hand side. So we can write the exponent of these coefficients times delta by a product. Since we have here a sum, in the exponent we'll have a product. Here we have a product over all the nearest neighbors. These coefficients with the delta inside, this is in the form 1 plus c delta. Okay, and from the interactions, we're going to get a product over all the interactions with this delta. Okay, this is just a writing of the right-hand side. Okay, so now we want to make contact with this random graph description. So we're going to first of all define subgraphs h of g by the following rule. So the subgraphs h are going to include all the vertices always, so they're spanning by definition. Okay, and how do we choose the edges of h? This is just like, this part is just like Fortune-Castellane. When we open the brackets here to form the products of just these terms, of the nearest neighbor ones, okay, forget about the gammas for a second, just these terms. Sometimes for an edge, we're going to choose the delta, and sometimes we're going to choose the 1. When we choose the delta, we'll declare that this edge is part of h, and when we choose the 1, we'll declare that it's not part of h. Okay? So this gives us exactly all the spanning subgraphs h of g, when all the terms that we'll get in this product are exactly in one-to-one correspondence with all the subgraphs h of g. Okay? So this is this term. What about this term? Sorry, let me first say one more thing about this term. Because of these delta, chronicle deltas, what they tell us is that we're going to get the same sigma, the same Potts degree of freedom along every connected component, right? For example, here, this is one connected component. If all these blue lines are part of the subgraph H, we chose them. That means we chose the delta. So sigma here is equal to sigma here, and is equal to sigma here, and so on. So in every connected component, we're going to have the same degree of freedom, sigma, the same value for the Potts degree of freedom. Okay, now we move to the second term, okay? The second term, we can similarly think about it as generating all the markings. Again, why? For every marking gamma, if we choose this term when we do the product, it means we use this marking, use this interaction. And if we choose the one, it means we're not using this interaction. Okay. Now, the problem is that at the moment we can still get markings which are not allowed, right? For example, in this case, we said that every tree must include exactly one dot. But when we take all the possible markings, we may get, for example, 2 dots in the same tree or something else, or no dots. So how is it fixed? This is fixed by the q goes to 0 limit. Why? Because notice that in every connected component of H, okay, if we use only one marking, because of this factor here, you see that here there is going to be a q to the v over 2. So if you have only one v at your connected component, you're going to get a factor of square root of q. And because of this delta, it will tell you that not only that all the spins are the same in the connected component, they're actually the same as the magnetic field H. So there is no sum over spins, they're fixed. So you'll just get a factor of square root of q. Now, if you had 2 markings or more, you'll still have no sum over spins, but you'll have a higher power of the square root of q because of this. So that will be suppressed when q goes to 0. Oops, sorry, 1 second. Yeah. Okay, so that will be suppressed when q goes to 0. The only remaining case is what happens if you have no markings at all. Let's say that in this connected component, you have no dots. In that case, you will not have the magnetic field. So you'll need to sum over the pot's degree of freedom, which will give you a factor of q. So again, it's suppressed, okay? So you see that the q goes to 0 limit tells you that all the markings are automatically only allowed markings. They're all correct, okay?
Could you just repeat why the one with 0 dots is ordered q?
Yeah, definitely. So for example, here, right, we said that because of these terms, all the pot's degrees of freedom are the same, right?
Mm-hmm.
So you need to sum over the value of sigma along all the vertices. There is only one sigma, but it still gives you a factor of q.
I see. Thanks.
Okay. So the trick indeed is that it's still smaller compared to the square root of q in this case. Okay.
Mm-hmm.
Okay, very good. Now, what is the value of every diagram? So at the moment, we justified why all the markings are correct. We still didn't justify why we get only forests, okay? So this is similar to what is usually done. We see that what are the factors of q that we get? We get either a factor of q from here or from here, right? So from the blue, we get a factor of square root of q for every edge, right? This is by definition. These are the edges. So we get square root of q to the power of number of edges in the subgraph H. And we also get a factor of square root of q for every dot. But the number of dots is exactly the same as the number of connected components, right? We said that there is exactly one dot in every connected component. So we get a factor of square root of q to the power of, to the number of connected components k of h. Okay. Now for any graph, the number of edges, any subgraph H, the number of edges plus the number of connected components is at least the number of vertices, right? For trees, clearly it's this. For forests, sorry, it's clearly the same, right? For every tree, 1 plus the number of edges is just the number of vertices. But if you have loops, you can have greater. The left-hand side can become bigger. Okay. So that means that because this is the power of q, if you want to minimize the power of q, since you take q to 0, you have to have an equality here. You don't want to have this to be bigger than v. You want this to be equal to vh. And so you get that this is equal to vh precisely for forests. So the q goes to 0 limit gave you 2 things. It gave you that all the markings are correct. There is 1 dot in every connected component. And there is only forests in the sum over subgraphs H. Okay. So now what you get is that here the factor of q to the vh over 2. Vh is the same as v, right? Because as we said, h is spanning. So it includes all the vertices. It's just going to cancel this factor. That's why we had this factor here. And so what we get is just what this description tells us is just that we have a sum over all the spanning forests. We have all the markings from opening these brackets, only the T gammas that are allowed, and the weights from these W's here, this term, okay? This is exactly the same as the first description of the fermionic theory that we wrote before. Sum over all the spanning forests, all the allowed markings, and then just the interaction coefficients times the edges of the graphs. Okay, so that proves the claim. This claim because we showed that the left-hand side and the right-hand side are given by the same random forest description. Is it clear? Any questions on this? This is the proof of this claim, which is the main point that I would like to make. Okay, if not, let me just mention that this classic case that I mentioned at the beginning of the OSP12 theory, in that case, we have OSP12 sigma model. It's dual to Q goes to 0 Potts model. We include only this kind of terms. We don't have any of these terms. Okay, so this is the question before, right? We have only these terms, only the nearest neighbor ones. This is just the OSP12 sigma model. And in the sum over spanning forests, we don't need to include any interaction. So again, this is just a special case. We will have only these terms. And here in the sum, we don't need any of these T gammas. We don't have any interaction. We just need to sum over spanning forests. No markings, just the value of every forest. That's it. Okay, but this is a generalization of this. Okay.
In this classic case, you mean would be the one by 20 years ago, right?
Yes, exactly.
Okay, yeah.
Exactly. Okay, so here I just describe a generalization of this. Okay. Okay, so now let's indeed apply this to OSP12M. Okay, so now indeed we get back to that. So we found something more general, but we can also apply it to this case. Okay, so what should we do? We as we said, I'm going to assume that the sigma model and this cubic field, not cubic, this field theory with the sigma field are equivalent. So I can choose any of them. So let's concentrate on the nonlinear sigma model. So we just have these kinetic terms for OSP12M, and we have this constraint. Okay, this is the definition of the sigma model of OSP12M. Now I'm going to relate it to a graph. Of course, we need to discretize the space, the d-dimensional space. So let's just take a cubic lattice with spacing A. Okay, so we're going to discretize space. And what we're going to do is just in this equation, you just can solve for sigma by this delta function and plug it back. So all you have remaining is only a function of the variables theta and theta bar. Okay, so you're going to get some fermionic theory. So you're going to get a fermionic theory that looks like this. Okay, what we have here, okay, I'll just say briefly, but the details are not super important. You're going to get a quadratic term, just as the theta bar L theta that we discussed previously. You're going to get a sum x and y are going to be space-time points in this lattice. A and B, AK and BK are just some constants that are right here, some coefficients. And you're going to get here one sum over all the lattice points. And here you're going to get a sum over all the nearest neighbors. Okay. And the W, the constant W here is essentially -1 over G squared. G is the coupling constant of the nonlinear sigma model. Now, the only important point about this is just that this is a special case of the general fermionic theories that I discussed, right? So this is just one particular case that we have here, right? You have just various interactions, T gammas, that will correspond to these interactions and to these interactions. So it is just, we can apply the results that we got there. Now, what is L? We need to still read off what is precisely the graph G, the total graph G for this theory. And the way that we read the graph G is from this matrix L by the off-diagonal components of theta bar theta, the quadratic ones. And what we get, of course, is going to be related to this cubic lattice. But what we get is that here I just demonstrated in 2D, is that we're going to get M copies, capital M copies. Here, just to remind you, there are M variables theta and theta bar. So you're going to get M copies of the cubic lattice. The different copies are not connected by an edge, and each copy, the edges there have the same weight W that is related to the coupling as I wrote here, -1 over G squared. Okay, so basically you have one copy of the lattice for every complex anti-commuting variable. Okay, so now you can apply basically the result that I mentioned, right? So you can give both the random forest description and the Potts description, living on this graph, right, of this theory, of the OSP1 to M theory. Okay, so a priori, at least, it was surprising that you could get a Potts description to this kind of theories, and we see that you can get a Potts description for many, many different theories. Now, let me specialize mostly to the case of m equal to 2. I will now say why it's basically the most interesting case. So the case m equal to 1 is the classic example that we mentioned of the OSP 1, 2. We know the random forest. We know the Q goes to 0 pots of it. We know everything, okay? Now, for the case m equal to 2, there are the field theories that Klebanov wrote, which I mentioned, right, these theories. Now, the m equal to 1 was the cubic theory. For m equal to 2, you see there is a fifth order, a quantic maybe theory. And just by dimension analysis, you can see what is the upper critical dimension where this interaction becomes basically marginal, is 10 over 3, okay? So for m equal to 2, the upper critical dimension is conjectured to be 10 over 3 because of this relation, which is just above 3 dimensions. Okay, in fact, it's not much more than 3, right? If you do 10 over 3 minus epsilon expansion, d equal to 3 is epsilon equal to 1/3. So you may hope that the epsilon expansion is actually very good for this theory. I think it's not obvious, but it might be true. I mean, it makes some sense. Okay. Now, the issue is that all the other theories, the m greater than 2, have an upper critical dimension that is below 3. Okay. So that means that all the other theories are trivial in 3 dimensions. So this is the only new theory, the m equal to 2 one, OSP14, which is supposed to give you a non-trivial critical theory in 3 dimensions. Okay, that's why I said that the m equal to 2 case is basically the most interesting one out of this series. Okay, the new interesting one. Okay, so I'm going to concentrate mostly on this one. Okay, so now we can apply the same claim that I wrote, the general one, to this theory, right? So we can take this fermionic description, this one, and just turn it into a Potts description. Now, one thing that is convenient is that since W goes like 1 over G, if you're interested in small coupling constant G, it's better to rescale theta and theta bar by square root of W. So we're going to rescale theta and theta bar to divide it by square root of W. Then we're going to use the duality that I mentioned in the main part of the talk, in the second part, and get that for every, what we're going to get is that for every lattice point, right, for every vertex of the graph, you're going to have one new Potts degree of freedom. Now, for the m equal to 2 case, we have only 2 lattices, right? So we have only 1 and 2. That's it. So we're going to get, for our original Euclidean space, for every point, we're going to get 2 Potts degrees of freedom. So sigma xi, where I goes over 1 and 2. Okay. And then, okay, here I write the full Hamiltonian for the Potts, just to make it very explicit. Okay, of course, the details are not very important. But you have, as you would expect, you have a nearest neighbor terms, okay? Just the usual Potts terms. And you have various interactions, higher deltas with the magnetic field. Okay? And the point is that if you're interested in weak coupling, when G goes to 0, this form is very convenient. Why? Because when G is small, you see that W is large, so 1 over W is small. And you see that all the coefficients here include inverse powers of W. This. They're all inverse powers of W in the interaction. So the log of 1 plus this is going to be small. Okay, 1 over W is small. So all the interactions, except for this nearest neighbor terms, all the interactions, this is like a kinetic term, are going to be small when G goes to 0. Okay, so this is a very convenient description of, it's a very explicit statistical model for this OSP14 theory. Okay, this is one of the main results. You see that you can do perturbation theory, you can basically do simulations, you can do anything with that, right? It's a very simple statistical model that should give you the same theory. Okay, so this is generalization of the classic case where Q goes to 0 pots with only such interactions only the nearest neighbors deltas, gave you the OSP12 theory. So here I show that the OSP14 and all the other OSP12M, and in fact much more general fermionic theories, are just deformations of this simple Q goes to 0 Potts model. Okay, this is a very this is just a nice generalization of the same result. Any questions on this Potts description?
Can I ask, maybe related to before? So
Yeah.
you're working now in 3 dimensions because you were saying that, yeah, this is hope that is non-trivial in 3D. But what about 2 dimensions? Can you have also the other theories that are interested in 2 dimensions, or for some reason you already know them?
Right. I think in 2D there is no. So in 2D like this. Right. It's a good question. I think in 2D, I think this theory, the nonlinear sigma model, is just it's asymptotically free. I think. Let's see. Does it have? I think it will not have a non-trivial. I think it will not have a non-trivial critical behavior. Yeah, I think these theories are defined above 3 dimensions. I think it will just be trivial at 2D. Like you can do a 2 plus epsilon expansion and find a fixed point, but when you take epsilon to 0, it will just be the trivial theory.
Okay, I see.
Okay. Yeah, so that's why I think, yeah, so if you're interested in integer dimensions, yeah, you have not too many options. So for the OSP12, you have 3, 4, and 5 dimensions. For the OSP14, you have only 3 dimensions. And for the higher ones, you don't have integer dimensions, only non-integer ones.
Yeah.
This is, I think, an important point. That's why I concentrate on this theory, but you can discuss also other ones. Yeah, but that is an important point. Okay, so this is the Potts description. Now let me again just interrupt me if there are more questions. Now let me also discuss the forest description. Okay, well, again, it's a nice statistical description, but it's also a nice exercise in the kind of descriptions that we gave. So what do we have here? So first of all, let me say for general M, it's very simple to say what are the interactions. They are going to be composed of these dots, right? But they're even simpler than that. So for any of this OSP1 to M theory, our prescription said that you need to sum over only spanning forest. That's already good. Now you need to say what are the markings, what are the interactions that you need to mark the various trees. So there are only 2 kinds of such markings. One is that you take a coordinate x in your original space, and now it's going to have m copies. So any subset of the m copies of the same coordinate is an allowed interaction. Okay. The second one is that you take a nearest neighbor pair. Okay. Again, there are m copies of the nearest neighbor pair, and you can take any subset of these m copies of nearest neighbors. You don't have to take the same in each copy. You don't have to take both of them. You have to take either 0, 1, or 2. You could do whatever you want. But the point is that you only take subsets either of the same vertex or of nearest neighbor pairs. That's all the interactions that you have. So here is I just show an example. For m equal to 2, you have only 2 layers. So you have various trees, okay, as we see here in blue. One kind of interaction is if you have one vertex in only one layer, okay? But another kind of interaction is the same vertex, but in the 2 layers. So this is like a non-local kind of interaction. It marks both this tree and this tree. Now, of course, it's important to have such interactions, because if we didn't have this kind of B2 interactions, then we just need to sum with the B1s, we sum over independently over this layer and this layer. So the result will just be a product of the m equal to 1 partition functions, but of course that's not true, right? So this is why you need to have this kind of interactions in general. Okay, so let's see. How about time? I think I have like a minute. What?
Yeah. 5 minutes. Yeah, it's fine.
Okay. So I'll just make one more comment, and then I'll be done. Okay.
Yeah, sure.
Okay, thanks. Okay, so the only other comment is that this kind of description, forest description, you could say that it's still a bit complicated, right? You sum over all the forests, but you need to include interactions that sort of, for every forest, you need to go over all the ways that you can mark it with the interactions. It's a bit complicated, right? It would be best if you could just say what is the value of every forest immediately, okay? Just as in the case of the OSP12, there you just say that the value of every forest is just the product of the edges, and that's it. So here, the only comment I would like to make is that you can do something like this also here. The idea is to use the same point that I made before, right? So the idea is that instead of marking with points, you can instead add the edge connecting them, and now you will have a marking not of the original two trees, but of a single tree with this edge included. So you're going sort of to translate your markings of disconnected trees by new trees where the marking is connected, okay? Okay, so this is just another way to phrase the same thing. Now, in this case, let's first discuss the case of only one layer. For one layer, you have two kinds of markings. Either you mark one vertex with weight 1, okay? Or you mark, as here, two nearest neighbors with the weight that turns out to be minus W. So what will happen is that if you translate this to this language, you now have one tree where you mark an edge with the value now minus 1, because the W is just the value of the edge. So what you get is that for every layer, if you just look at one of these layers independently, you sum over the vertices with weight 1 and over the edges with weight minus 1, and you get that the sum over the vertices minus the edges is just 1. So every tree, you don't need to sum over all the weights to mark it. It's just going to get the value 1, okay? Now, you have two layers, here the upper and the lower layer, and you can do the same thing. I'll just show one example. If you have a vertex here and the vertex in the lower layer, you're going to introduce, previously there are no edges connecting the two layers. Now you're going to introduce an edge that connects the two layers. But now the marking is just this guy, and that's it. So the whole point that I would like to make is that even in this OSP14 theory, the prescription that you're getting is very simple. What you need to do is to sum over all the spanning forests, okay? And now every tree is either embedded in the same layer as here, okay, tree only in the same layer, or the tree can have one edge, up to one edge that goes between the two layers, either an edge that connects the same coordinate or nearest neighbors one, okay? Like this is the same coordinate and this is nearest neighbor. So these are the only three kinds of trees that you have, either embedded in the same layer or one edge connecting the two layers, either to the same vertex or nearest neighbor one. And now the weight that you're assigning is immediate. You don't need to go over all the markings. For a tree, as I showed in the previous slide, here, for every tree that is embedded in the same layer, the weight of the tree is just 1. If there is one edge that goes to the other layer, but in the same coordinate, it's just minus W. And if it goes to the nearest neighbor one, it's just some very simple formula, which is just depending on the degree of the vertices. Okay, so for every tree, you just assign this value that I said, and the product of the weights as usual. Okay, so this is again just a simple generalization of the OSP12 case. You don't really need to go over all the markings. You can just assign an immediate weight to every forest. Okay, is it clear? Or any questions? Okay, the point is just that this is a simpler description that again is easier to simulate. Okay. Okay, so now let me summarize. Indeed, so what were the points? The point is that we started with this classic example of the OSP12 sigma model that is known to be equivalent to Q goes to 0 limit of pots. We wonder if it's true for OSP12M sigma models. In fact, we showed that there is a much more general duality between fermionic theories that I proved and Q goes to 0 pots. Okay, and that shows us that actually the pots model, when you take Q to 0, it has a very, very rich phase diagram, right? It can describe so many different theories. including all these fermionic theories with all the allowed interactions that I wrote. And now just mention one future direction. These field theories that I mentioned, that Igor studied, they give some predictions for the OSP 1 to M theories, as we discussed, right? They said that the M equal to 2 theory exists in 3D, but none of the higher ones. And this needs to be verified. So, for example, the methods that we discussed here with the Potts model and the random forest models, they can be useful to check these claims. And that's it. Thanks. Thank you.
Great. Maybe can I start asking about your last point? So, I mean, you show all these dualities and so on, but can you also explicitly compute the same quantity from different directions and then check that it's actually true? I don't know if it makes sense, my question, like...
Yeah, like some specific, something like, yeah. I mean, the partition function is very hard to calculate, right? I mean, it's still a sum over... Of course, you can do some various, finite lattices, finite graphs.
Yeah,
and
yeah.
Then, of course, you could do that, and and then it's, well, it's basically guaranteed to be the same, yeah, but indeed it's...
Okay, so you can do something in this case, okay?
Yeah, but indeed, I mean, I didn't do any example like literally explicitly, right? Writing what is the formula as a function of the weights, right? I didn't do any of them explicitly, right? I guess you can get pretty non-trivial results and see that they agree between the different sides, especially in the OSP 1 to M. It's actually very hard. Yeah, that is something that is very nice to do. I mean, I didn't do it. But whether you can do some, in like the statistical description, whether you can do some random phenomena and compare them to some, I mean, like a critical phenomena, compare them, whether you can explain some exponents, right? That would be very nice. I didn't do that. That would be very, very nice. Yeah.
That would be, you're talking about some OSP, and the other side would...
Right. Because, for example, like in 6 minus epsilon in the OSP 1, 2, or in this 10 over 3 minus epsilon, you can certainly calculate scaling exponents using the field theory. And then you can, in principle, try to argue from the statistical description why you get these exponents. I mean, that would be amazing. I did not do that. That would be very nice if it's possible.
I see.
Yeah. From the pots or from the forests. Yeah. That would be amazing. Yeah, I did not think about that.
Thanks. Any other question from Zoom also? Okay, I guess not. So let's thank Vladimir again for the talk.
Thank you so much.
Thank you a lot, Vladimir. And
thank you very much. I'll stop the sharing.
Yeah. Thank you a lot, and see you guys next time. Thank you a lot for coming.
Thanks.